Well, good morning. Um, the big thing today is we're going to learn another form of proof. So before we do, I want to do a little bit of background, a little bit of notation stuff, just so we kind of get used to things. We introduced the summation and the product symbols last week, so that if I had a summation of stuff or I have a product of a bunch of stuff, it was really, really easy to write things. So now I'm going to introduce two more symbols that basically mean we're going to do a bunch of stuff. And that is the union and intersection symbols. You say, but I already know what those mean. Oh, but we're here, we'd say from I equal 1 to n. And here we might say from I equal 1 to n. And now here we're going to say from I equal 1 to n and I equal 1 to n. In other words, we're going to treat these as operators, not just logical connectives. If I said A intersect B, I understand exactly what that means. This says I want to find the union from I equal 1 to n of n different sets. This says I want to find the intersection from I equal 1 to n of n different sets. Now that's new. So let's start with something really, really simple. Okay. Let's say that set A1 is 0, 1, 3. Let's say that A2 is 0, 1, 4. And let's say that A3 is 1, 2, 3. Okay. I would like to find the union from I equals 1 to 3 of AI. And I would like to find the intersection from I equal 1 to 3 of AI. It's a simple exercise to see if we understand what's going on here. Now, remember, union is a collection of everything. Okay, one big set. So if it helps you think of these could be people, these could be names, these could be items. So what items, in this case, numbers, if I put all of the sets together, well, do I say 0 and 0, or do I just write 0 once? Anybody want to try that one? How many times do I write the 0 since it shows up in multiple sets?
Just twice.
Do I write it as 0, 0, 1, 1, 1, and so on? What do you think?
Just once.
Yeah. So let's put it another way. I have a class roster for this class. I have a class roster for my calculus class. If I put the class rosters together and there are people in both classes, I don't count them as two people. I count them as still one person. So how many people are taking both classes? So I'm going to write everything. I'm going to have 0, 1, 2, 3, 4. Putting them in order does seem logical here. Okay, everybody cool with that? Now, is there an element that is common to all three sets?
One.
Only
And
the one.
yes.
And it's a set. Now, it's very important that we recognize these answers are sets because I'm finding unions and intersections of sets. Now, there's nothing complicated about this. I'm just introducing a new operator. So the summation and the products are operators because they're giving you an instruction. They're saying add up the terms, the next one multiply the terms, the next one find the union of all the things, and then the last one find the intersection of all the things. That's a pretty simple notion if you think about it. So that's a very simple thing, and there will be exercises both in the text and on the quiz dealing with that. Now, excuse me, I want to go a little bit further then. Now, in terms of notation and in terms of what things actually mean, we've been dealing with the logic of statements so far. So if I said P and Q, P is a statement. P is, I am going to the store. Q is, I'm going to play basketball. So P and Q is, I'm going to the store and I'm going to play basketball. That's it. There is no set. There is no numerical value. Okay. There's only statements. Okay. There's no math associated with a statement. So it is or it isn't. So if I said not P, okay. If P is I'm going to the store, then this is I am not going to the store. Again, there's no mathematical value. There's no sets. There's no elements. There's nothing like that. This is what we've been doing. Now we're going to segue over to sets, actual collections of things, whether they be finite or infinite. And now we want to introduce what is the notation if I want to basically say the same thing, but now I'm talking about sets. So now we do use different notation. So if I had set A, and A would be a collection of things like we just did a moment ago, and I have set B, then if I wanted to know what are the things, okay, we've done this before. These are no longer statements. These are actually collections. Put anything in there you want that makes it easy to understand. A might be my roster for the calculus class. B might be my roster for the discrete math class. So this would represent the collection of names that are in both. Over here would be the people that are in one but not the other, and then same here. Out here are the people that aren't in any, depending how big my sample space or my universe is. So this area right here, that's called the intersection. So we indicate that with a downward symbol B. We do not use this. This is for a logical statement. This is when I'm talking about I went to the store, right? This has nothing to do with this in the same context. This is how I talk about the intersection of sets, the collection of things that are in two sets at the same time. Again, that's not the same as a statement. That's why we use different notation, just so we can make sure we're talking about different things. Now, if I said all of the things that are in either one of the sets, okay, that's the union. And we write that. And hopefully we're all familiar with that, okay? Now, I'm also going to introduce another symbol that you've never seen because the context hasn't been there. What if I only want, sorry, this is hard to read. What if I only want this stuff? I want the stuff that is in A, but not in B. Now, how do I get that? I want the stuff that is in A, but not in B.
Would it be A union, not B?
So we're going to figure this one out because this is very important, just like this over here. So the first thing I'm going to do is in statements, if I did not go to the store, we just put a little squiggle in front of it and said, I did not go to the store. P is I went to the store, squiggle, I did not go to the store. The squiggle means not, and it is the appropriate term when you're giving statements, right? My water bottle is full, my water bottle is not full. There's no set, there's no collection, there's no numerical value, there's no calculation. But now when I'm talking about things, how do I talk about all of the things, let's say, that are outside of A? There's a different term we use, and that's when we use the term complement. Now, negation and complement do go together because they mean very similar things. There's only two possibilities. I either go to the store today or I do not go to the store today. So all the things I could possibly do today, the complement of all the things I could do, if you could list every conceivable thing I do today, make that infinite list. In one such situation, my list would have, I go to the store today. And the other list that is infinitely long is, I did not go to the store today. And all of those things. See, I'm now talking about doing it as a set. So the other set would be the complement of the first set. So a negation, in a sense, can produce a complement. A complement is actually a list of things. A complement is a set. So we don't use negation when we're using complement. We're saying, I want everything that's not in A. And the way we say it, the complement of A, we just say a complement. Now, different books and different courses will use different notation. If you've ever had statistics, that's not the only way we use complement. In statistics, we often would write it maybe A with a bar over the top. That is acceptable notation. If your stats book is using that every time they mean complement, great. There's no ambiguity whatsoever. In this class, we use the C for complement. So I have A and I have A complement. And excuse me, if I call the whole set, everything that I have, we often call that the universe. I like the term universe. So everything here is the universe. In a statistics situation, we would call every possible outcome the sample space. So some of you are familiar with the term sample space. It's the same thing. The sample space is every conceivable outcome that could happen. When I talk about sets and I say the universe, that's everything possible in my sets. not the literal universe. The only problem with universe the only thing I don't like about universe is we use a capital U. And what's the problem with using a capital U in this context? Anybody?
The union.
Yeah, some of your capital U's may end up looking like a union. So when you're making your union, don't put a tail on it. When you're making your U, make it really clear that it's a different symbol. And that can be an issue if you're not paying attention. So this is an absolute mathematical statement. A union, A complement is always the universe. Because that's every conceivable thing. Right, I have all of the people in the class, union all the people that are not in the class. Now that's all the people. Now, what about the intersection of A and A complement? Well, first of all, how many things? I'm talking about sets, so I'm talking about list of things. How many things are in a complement? Or excuse me, in the intersection here, sorry. How many things are in that intersection?
0.
Yeah, there are no things in that intersection. So if I have an intersection with nothing in it, I have a set with nothing in it. What do we call that set? The set with nothing in it. There's a term we use. You may know?
The
No
empty
clue.
set.
The empty set, good. The empty set. Now, the problem with empty set is there's multiple ways that people will indicate empty set, and it can be a little bit confusing. My personal favorite is to actually write a set, that's a terrible set, a set with nothing in it. That's sort of the universal empty set symbol. There is another symbol that is commonly used just out of laziness. People, and this is my least favorite symbol. It's generally called the null set, which is the same thing. The problem with that symbol, if you're in Calc 3 and you see that symbol, you can only read it as one thing. The angle phi, the angle between the z-axis and any point. I have students, particularly you vets, what do they use this for 100% of the time?
A 0.
Number 0.
A 0. By the way, a 0 should never have a line through it in any capacity ever in the history of the world. I had a student last semester use that for a 0 and use that for empty set, and often they come up in the same problem in the same context. And I'd say you cannot use the same symbol to mean two things that have absolutely nothing to do with each other. Yeah, I've never used that symbol in my life to indicate anything other than, and by the way, when I do it in calculus, I actually do it the usual cursive way. I put a little symbol through it. Okay, no, don't use that symbol because a lot of you use that symbol for multiple meanings. Now, my favorite thing about that symbol is particularly in an algebra class. You're solving an equation in algebra. Sometimes the answer might be x is 0. Sometimes the answer might be there's no solution. You are finding the slopes of your lines, and sometimes you might have a vertical line and the slope is undefined. I've had more students than I can count will use that symbol for a 0, for undefined, for DNE, for no solution, for empty set. By the way, there's absolutely no overlap of any of those statements. In fact, they don't even come from the same galaxies. Yet I will have people use that symbol for every possible answer you could give, because it's like a default. I'm going to put that down and hopefully the instructor will, give me credit, because they'll say, oh, that's what they meant. Never use that symbol. Just use empty set. Just keep it simple. So empty set means there's nothing in it. And this is a legitimate set. This is important to recognize, because something and its complement cannot have anything in common. In fact, that's where the term contradiction comes from. The term contradiction is when something and its complement are both claimed to be true at the same time. In logic, it would be something and its negation. P and not P cannot simultaneously be true. P or not P absolutely has to be true. Oh, that was the tautology contradiction thing. So I want this stuff here. So first of all, can I think of this as an intersection? My orange. Now that we've defined complement, can I think of the orange area as an intersection?
So would it be A intersection complement of B?
A intersect become perfect answer. That's absolutely perfect. That's it. That's what it is. Now there's another way to write this, and that's why I wanted to do this. There is another way. We actually are going to introduce an algebraic symbol into sets, which just seems completely warped and weird. Okay. And I'm going to give you a little background because I want you to be very comfortable with the notation. I don't want you to have to relearn any part of mathematics, but there's certain notations that translate universally that sometimes seem out of place. And I'm going to introduce something that seems entirely out of place. Let me go back to an algebra statement in a moment, okay? In baby algebra, I've got f of x equals, 1 over x minus 1. And I want the domain of this. Think algebra for a moment. I want the domain. In words, what would we say?
The domain would be from negative infinity to
No,
infinity with the
in
exception
words,
of
in
x.
words. No, you're giving me math. How about just keep it simple? We're on the phone, and I said, what domain did you come up with? What would you say?
Everything
All-
but x except x equals 1. Everything
Everything
but
but
x
one.
equals 1.
Wouldn't you say the domain is all real numbers except one? Would
Yes.
you agree? That's what you would say. Now, if you wrote it as an interval, you'd say, okay, the interval was negative infinity. Oops, sorry, wrong symbol. I'm thinking set still. Negative infinity to 1, union 1 to infinity. But most of us just like, all reals except one. Okay, great. Now let me throw a what if at you. What if my domain or my problem was something like this? Okay, I've got 1 over, x plus 3, x plus 7, x minus 4. I'm still multiplying down, x minus 10. Okay, now it's my domain. Do you really want to give interval answers now? Ugh. I'm going to have interval union, interval union, interval union, interval. Let's suppose I have like 25 factors here. Do you want to give an interval answer? The answer is, of course not. So let's go back to our language. You'd say all reals except all of the things that made the denominator 0. Do you agree with that statement?
Absolutely.
But how do you do that mathematically? There's actually a mathematical way of saying that. And the mathematical notation would be this. The set of reals backslash means delete, means remove. In this case, I'd say -3, -7, 4, 10. It also, you can write it this way, which a lot of people like better. I'm actually using a subtraction symbol. I'm saying the real numbers and I am subtracting the set that includes those 4 elements, meaning my answer is all real numbers except those 4 numbers. Now, personally, I don't care which one, by the way. Personally, I like this better than the interval because the interval is too long and too cumbersome and requires too much interpretation. If I had 20 different places where the denominator was 0, it's much easier to just list the 20 numbers rather than rather than 21 intervals technically. Oh, so this is called set subtraction and is absolutely valid and legal. So going back to here, there's another way of saying this. I'm showing you this because this is where we first introduced set subtraction, but it doesn't come up very often because we would just say this in words anyway. But if I want to do this in terms of sets, what did I subtract from A to get the orange?
A minus B then?
I'm say A minus
B?
A minus B. You could say this is simply A minus B. Oh my goodness, it's that simple. I have said A, I want you to remove everything B-ish. How's that? B-ish, that's a word. I have all of A and I'm removing anything that has B. And that would be this. This is an identity. It's not a formula, it's an identity. It's how we're defining set subtraction. And so which one is considered simpler? Well, usually, strangely enough, usually this one is considered simplified because I can then use other things like commutativity, associativity, distributive property, De Morgan's laws. I can use all my laws on unions and intersections. I can't use any of my laws on set subtraction. But these are equivalent statements, and it's very important that we recognize that just for the purposes of the algebra of manipulation. So if I had something that looked like this, I'd know what to do. Now, what we want to do today, the big picture of today is we want to do what are called set algebra in a sense. I want to know what can I do with sets, not just unions and intersections, but if I wanted to combine things, How do I do it? How do I show one set is contained in another set and vice versa? That's not an obvious thing algebraically. So here's the way it works. I want to prove set A is contained in set B. I have two sets A and B, and I want to prove set A is contained in set B. How do I do that? It's actually simple. It's called an element proof. But remember, these are sets, so they have things. So what I want to do is show if X is an element of A. Just take X, any element. This, and now we use this implication symbol, not the arrow bar anymore. Now's where we use this because we're actually doing something a little bit different. If X is in A, this would automatically imply that X is in B. So for every value, or for everything in A, it automatically would be in B. If I can show this, then I've shown set containment. Okay. If I want to show that it's not the case, then I would do something different. Now, what if I want to prove two sets are equal? Now, this is one of those ambiguous statements again. A set is a collection of things. How can two sets be equal? Anybody want to try that? Because we've talked about this before. How are two sets equal since a set isn't a number?
They have the same elements.
Yeah, they contain exactly the same elements. They're identical. I have a class roster with all your names, and then I have a different class roster with your same names just jumbled up. They're the same set of names. So I'd say the sets are equal because they contain exactly the same elements. One does not have more than the other or anything else. And by the way, where that can be a little bit ambiguous is if your sets are infinite. You know, how do I show that? So that's one of the things we're going to tackle. If I want to prove this, the way I do it is I show A is contained in B and B is contained in A. To prove this one way, I just have to show the elements work this way. But to prove this, I've got to do both of these, meaning I do two sets of element proofs. That's what it means. This is a much bigger problem because it means you have to do an entire problem twice. But realistically, one way and the other way are probably going to look very, very similar. Okay. So this is the structure of what we're going to be doing. We're going to be showing containment or equality of sets. And the only difference is the equality of sets, I just have to show containment twice. And this is how we show containment. So I'm going to throw a what if at you, because we want to be able to break it down because we're going to be using complements and different things. And I love using a Venn diagram in this context because I think the visual sometimes is so much easier than the abstract. All right, here's my set A, here's my set B. If I said that X is an element of the complement of A union B. X is an element of the complement of A union B, then where does X live?
And in A and B except the middle part. Then
You guys agree with that one?
just kidding, never mind. I thought it was an intersection.
You just mess with us to see if we're paying attention. Well, first of
Yeah, I
all,
thought-
A union B is all of this. So what's the complement of A union B? Wouldn't it be the outside stuff?
Yes.
So
Yes.
if X is an element of A union B complement, where does X live? Out here somewhere. Do you agree?
Yes.
Right. So what would be true about, is X in A? Is X not in A? Is X in B? Is X not in B? So for that statement, I'm write like this. I'm giving you some of the foundations you're going to use to prove. What must be true if this statement is true? Well, certainly X is not an A.
X is not A and B.
So X is, now how do you say X is not in A?
Would you put a slash
It's-
through the element?
Exactly. X is not in A. Anything else?
Comma
If
B.
X is not in A, it means X still could be here. So would X not be in B also?
Yeah, so just comma B.
X not in B now. I'm going to leave a little space here. There's a word there. It's real important. There's only two possible words that could go there. What are they?
And or.
And or. And by the way, it's a planet killer if I get the wrong one. It's an absolute
and.
failed conclusion. Is it an and or an or?
And.
It's got to be an and because I am not in A and at the same time I'm not in B, therefore I'm outside both of them. If I said I'm not in A or I'm not in B, then I could actually be here or here, couldn't I? If I'm not in A, but I am in B, I'm here. If I am in B, but not in A, then I'm sorry, if I'm in A, but not in B, I'm here. If I put an or, all I'm doing is removing the intersection. I don't want to be in any part of either one of them. So this is really important that I use the word and here. So to not be in the union or the complement of the union means I'm not in A and I'm not in B. All right. If X is not in the complement of the intersection. Ooh. Now, or I'm sorry, X is in the complement of the intersection. Now, where's the complement of the intersection?
That would be A and B without the middle.
So that's everything except this. So
Yes.
okay, everybody cool with that? I'm everything but now. That means that if X is not in there, then X, well, it can't be the same statement. But if I'm not in there, then I'm not in A intersect B, but I already said that. I'm not in A. I'm not in B. I'm not in A, but I could be in B. If I'm not in A, but I can be in B, I can't be here because I'm not in A. So if I said you're not in A, but you can be in B, then this is okay. I'm not in B, but I can be in A, this is okay. And I'm not in either one of them. That would be an or. I'm not in A or I'm not in B. If I'm not in A, then I cannot be in the intersection. Do you agree? If I'm not in A, then I can't be in the intersection. If I'm not in B, then I cannot be in the intersection. So one of those statements has to be true. I'm not in A or I'm not in B. If either one of those statements is true, because it's an or, if either one of those is true, then I can't be in the intersection. If both of them are true, if I'm not in A and at the same time I'm not in B, then I also get all the outside stuff. So this, boom, this, boom. These are absolutes, which are really, really important because I want to show now, I want to be able to do an element proof. We're going to do one from beginning to end. They're not hard at all, but sometimes we don't know what route to take. And that's really the whole thing is how do I know what to say and when to say it and all that? So what I want to do is take one of De Morgan's laws and prove it because De Morgan's laws are not only probably the most important when it comes to logic and sets and everything else, but they're probably the most straightforward when it comes to proving things. So let me see which one I want to do. I think I want to do this one. Hold on. I want to prove, okay, we're going to prove so I wrote it down. A union B. I want to prove this. Okay. Now we know this is true. This is one of De Morgan's laws. We know this is true, but that's because we were told this is true. We actually want to prove this is true. Ooh. Now, I am not really that interested in you doing both pieces of the proof. I'm going to do one of them and then the other one's probably going to look similar, but I want to start from beginning to end. So what we're going to do is start by doing the containment. Okay. So the first thing we're going to try to do is show that this is contained in this. I'll put in parentheses. Here's our first step. I want to show containment in one direction. And what I said earlier, that means I want to show that any element that is in this is automatically in this. That's how we'd show containment. once I can make that conclusion. So the way we start the proof is we say, let X be an element of the complement. That's my first step. My conclusion, if I do it right, my conclusion should be, and then X is an element of that guy. Okay, so excuse me. So if X is an element of the complement of something, then what does this automatically imply? That X is not an element of what? If X
A
is an
and
element
B.
of the complement,
A and B.
And
no. If X is in this set, then X can't be in, what's the complement of this set? You guys are overthinking. You're actually doing math.
X
X
can't
is
be
an element
A.
of the complement. Right now, I'm saying X lives out here. Therefore, where doesn't X live?
X
A
can't live
and
in A and X
No,
can't live in B.
No. The definition.
oh,
Complement. You're overthinking. If X is in one set, then it is not in its complement. If X is in the complement of a set, then it's not in. Yeah, there's no ands or ors. No, just the exact same sets. X lives in the complement. Therefore, X doesn't live in here. X lives in the complement of the union, so X doesn't live in the union. That's what complement means. Yeah, don't overthink that one. This is a nice one. Now, X is not in the union. So if X is not in the union, then what do I know for certain? If X isn't in the union, then it can't be in either one of them. Do you agree? X is not in the union. So what does that imply? That X is not in A, X is not in B. X is not in the union. So it's not an A. Is it an or is it an and at this point?
and
It's not an A and it's not in B because in my picture, X is out here somewhere. It's not in the union. Therefore, it's definitely not in this. And at the same time, it's not in this because the or would allow part of the wiggle room there. Nope, that's definitely an and there. I'm not in either one. This is where, again, a picture sometimes helps. Now, if X is not in A, then where does X live? If X is not in A, where does X live?
the universe.
If X is not in A,
A
what's
complement.
A complement?
A
yeah,
complement.
okay.
All right, starting to get
it. That's kind of cheating. It's somewhere in the universe. We just don't know where. X is basically Loki, right? Just bounces around the universe, I guess. And if X is not in B, then X is in B complement. That's the way we go back and forth. Oh, if I'm in a set, then I'm not in the complement. If I'm in the complement, then I'm not in the set. That's what complement means. So I started with X in this, which means X isn't in the, which means that, which now means that. Now I'm telling you X is in this set and at the same time X is in this set. Therefore, what set must X be in? If it is in these two sets simultaneously, it must be in their, what?
Intersection.
Must be in their intersection. Does that make sense? I am in two sets simultaneously. That means I'm in their intersection. Is this a good thing?
great thing.
I started by assuming X lived in this set, and what have I concluded? That X lives in this set. Therefore, we now can say A union B complement is contained. Sorry, my containment looks like a less than or equal, sorry. Contained in. Now, kind of fun. Wasn't hard. And again, when I do things right, it kind of self-navigates. Where people have the most trouble, though, is the ands and the ors. A is in this, excuse me, X is in this set and X is in this set. That's where the intersection comes from. If I mistakenly put an or here, then I would have put a union here and that would not have worked. That would have been an incorrect result. That's why I've got to be really careful with my language and making sure that what we're saying is accurate. If I'm not in a union, then I'm not in either one. That's why that was an and. But that and carried down to this intersection right here. Now, how would the other half go? Well, we'd start the same way. I'd start with X being in here. So if X is in this intersection, then X is in both of these at the same time, which means X is not in either one of A and B, and we'd go from there. So kind of cool. Okay. Any questions so far? I'm gonna do more stuff in a moment. Everybody cool with that?
Nope.
Now, I want to do one now involving let's see, which way do I want to go? Oh, okay. We just came up with basically a formula for set subtraction. I actually want to prove it. I stated it, and it was kind of, when it comes to De Morgan's laws, we can draw a picture, and the picture makes perfect sense every time. And it should make perfect sense. What we just now proved, let me figure, I erased it, hold on. We just proved okay. I started with, well, we did the containment. We didn't actually do the entire proof. I used the complement of A union B. What is the complement of A union B? We agreed that it was everything out here. That's the complement of A union B. That's not really a stretch. Now, what was that? What did we say that was? Well, we said, let's consider A complement. Now, what is A complement? I'll do that in orange. A complement is everything outside of A. That's A complement. That's the orange. Okay. Everybody cool with that? What's B? What's B complement? That's everything outside of B. Oops, sorry. B complement is everything outside of B. Now, if I said A complement intersect B complement, that would be where the orange and the blue both coexist, isn't it? Okay.
Yep.
Where do the orange and blue coexist? Only on
Everything but A and B.
So in other words, from a pictorial standpoint, I started by drawing the picture of this. That was the black. That was everything on the outside. I don't have that many colors. Then I said, well, what's A complement? I think I said that was the orange. What's B complement? That's the blue. Where the intersection is where I'm orange and blue simultaneously, which is the exact same region. That's why we know it's true. Now, that is basically one of these, I'm doing this to convince myself of its truth. That's not a proof, but it's convincing that I say, okay, I believe it, because if I got any of the unions or intersections in the wrong place, then I would have a picture that said, no, that's not going to work. That clearly can't work. So what we want to do now is do the set difference. We convinced ourselves that that was a true statement mathematically. Okay, we convinced ourselves. Now I actually want to do the formal. So, and again, I'm just going to I'll do the one-way containment, because if you can do one way, you can certainly do the other way. We're going to do A minus B. I want to prove A minus B is equal to A intersect B complement. That's what we just said a few minutes ago. So let's start with, so we'd say let X be an element of A minus B. So then what does that mean? Where does X live? If X is in A minus B, then I know that means X is in what? It is in which set?
In A.
It's in A, and at the same time,
Not B.
not in B. Good. Now, the problem is when you're doing a set proof, X not in B is a powerful statement, but I can't use the things it's not in to get to my next statement. So not being in B means it is where?
The
Can
complement.
you say
of
that
B?
again, Professor?
If X is not in B, then where is X?
Got it.
It's
Okay.
in the complement. Okay, so in other words, in order to perform my proof, I have to use the places where X is. That's a powerful statement, but I can't do intersections of not in sets. I can do intersections of complements. So this implies that X is in A and X is in B complement. Now X is in A and X is in B complement. Therefore, X is in what? It's in both of
This
these
is
at
an
the same
A
time.
intersection complement B.
And I believe that's what we wanted to show. Like, cool. So, well, that was pretty simple. Yeah, but I still have to show it. So element proofs are rarely complicated. Okay. Where an element proof can get a little bit tricky is when you have more than two sets. Okay, that's, and I by the way, I have posted notes on element proof. I know no one's probably noticed them yet. I just kind of walk you through a couple of them and say, here's the basic structure. An element proof when you have more than two sets can be a little bit trickier. So I really want to concentrate on the two set problems. We will get to the three set problems over the next day or two. They're not, it's not that they're terribly difficult. It's just, there's just a little bit more going on. So the idea with an element proof is, if I'm trying to prove containment, then I start by saying, let X be in the first set, take all the facts and, hopefully that leads to X being in the second set, then I'm done. If I'm trying to show equality of sets, I do the exact same thing, but then I do it again in reverse. I start with X being in the second set, and I show that leads to X being in the first set. That's it. But because of this, we can prove very, very powerful mathematical statements. So element proofs are a very, very specific kind of proofs. It's how we prove set containment and set equality. We didn't use this when we were talking P's and Q's and statements. Because statements, there's no elements in a statement. We don't say statements intersect, right? There's no unions of statements. I can have an and or an or on a statement. I went to the store today, or I watched TV. That I can say that, but there's no list of things where I'm comparing, overlapping, and that sort of stuff. So when we say, I'm going to make a series of statements and throw some negations in there and some ands and ors, and is it equivalent to another series of statements? Those are the type of logical equivalences we went through. Now, all of the things that we did with the P's and Q's and the logical equivalences, there are versions now with sets. So in the text, if I can find it, I know it's in here somewhere. In the text, let's see, I think it's section 6.2. Yeah, in section 6.2, I'll just hold it up. You've got a lot of the same kinds of stuff that we had with the P's and Q's, but now we're using unions and intersections. And the really obvious ones, stuff like, like really obvious stuff, A union B is equal to B union A. Whoa, what's commutativity of union? Oh, okay. Right. There's some really simple ones. Let's see, what would another one be that we should actually be very familiar with at this point? What about, and by the way, some of the language will be a little bit different this time though. Let's do, okay, I have A union B intersect C. Can I write that correctly? A union B intersect C. What does that look strangely like?
Like the distributive.
Yeah, so that is the distributive property. So wow, that's crazy. Can we prove that? Actually, we can. But we always want to convince ourselves of its truth. So when we have three sets, you generally are safe drawing it so that there actually is a three-way intersection. Now, is it possible that some of these intersections can be empty sets? Is that possible?
Yes.
Yeah, but if you start by making the sets disjoint means non-overlapping. If you start with that, then you're starting by assuming intersections are empty, and that can be dangerous because they might not be. So B intersect C is that. I want A union B intersect C. So I want all of A and that. Oh, so I got all of A and this little extra piece here. Okay, so now let's look at it from a different point of view. A union B. A union C. What shows up in both That's the black and the blue. Well, that would be all of A and this little extra piece. That's the only part. Oh, that was the same as the first one. Again, this is not a mathematical proof. This is sort of like I'm convincing myself that this is actually a true statement. So we have similar things, but now what we don't have, okay, in the other one, we had negation laws because we were using a negation symbol. We don't have negation laws here. Now we have complement laws. So for example, and again, I want to make sure we understand the similarities, but also the differences. Question?
I got a question real quick, Professor. If you just have the A at this point, would the A be the entirety of A, or would A just be everything that is A that doesn't get overlapped with B and C?
Well, this is just the entirety of A, regardless.
The entire.
Yeah.
Okay, thank you. Yeah, I just had my
Because
brain
now
was
I'm
starting to-
gonna, I want to combine it with other stuff.
Perfect.
Yeah, that's,
We're on there.
the problem is if I try to interpret it and not just take things at face value, I might make an error. So let me write down a couple of these. Okay, here we go. I've got A union A complement, A intersect A complement. Okay, let's start with these guys. Now, these are easy. A union A complement, that's the everything. And we said we're going to call that our universe. A intersect A complement, we said that we're going to call that our empty set. Okay, we know that that's what it means. You can't have an intersection with your complement. Now, what was the analogy with the P's and Q's when we had logical statements? So we'd say P or not P. Here, what do we call it? P and not P. What did we say when it was P or not P? Didn't we say that was that? And that was that?
Thank you.
This is a tautology. This is a contradiction. We said P or not P is absolutely always true. Doesn't matter what P is. That's what tautology is. It's always true. Oh, P and not P is absolutely impossible. Can never happen. That's a contradiction. So with symbolic notation of statements, this was called the negation laws because I was using the negation of P. The analogy with sets is I'm no longer using negations. I'm using this set and this set's complement, which are now measurable things. And I'm getting the universe or the empty set. So hopefully you see the analogies. This is called the complement laws. These are called the negation laws. They're similar. There is no negation. The word negation does not appear in any capacity with sets. But we don't use the word complement with statements. We use negations. But complements and negations, clearly, they have similarities. They go hand in hand, but it's a context thing. Statements, I can negate a statement. The complement of a statement is a little more ambiguous because I think of a complement in terms of sets usually. You know, if I was talking about a number line and I said, what is the complement of all numbers greater than 0? You'd say all numbers less than or equal to 0. But that's also in the negation of the statement, X is greater than 0, X is less than or equal to 0. So in certain numerical capacities, they're almost interchangeable. But in terms of sets, we only use complement. And I'm saying that because a lot of times a lot of people use this. They do everything right. And then I'll say, well, what rule did you use? Oh, I used the negation law. Well, there's no negation law with sets. That would be the complement law. But I still have idempotence and absorptions and all those other crazy ones. Okay. Now, that's as far as I wanted to get today. This should be relatively simple stuff. Now, what I've done on the quizzes and what I'll be doing for a short period of time, I have to change the way I load things on right now. What I have found over the last couple of years is some of your computers are really, really archaic. Your cell phones are completely worthless in this regard. That none of the symbolic notation translates on a lot of your devices. On a good computer, everything translates. But if I don't change some things and I send this to you, you won't see any of the symbols. In other words, they will be deleted from your screen, or worse, I call it the hieroglyphics. You get little weird symbols that, I don't know, maybe a bunch of little squares or a bunch of little triangles. You just get weird symbols that your technology is going to insert instead of what's there. And I found this out when students were saying, I can't tell what you're sending me. I have a weird symbol B. And I said, no, it's just a union. And I realized that some of your devices Sorry, but that's how you know you have really, really, really bad technology when your device can't translate simple symbolic notation. So I've saved everything that we're doing in this regard as a PDF. Then I sent that to you. Now, I'm pointing this out is some of this stuff can slip by me. Some of the stuff I may not have saved as a PDF. And so when you go to open it, you can't read it on your device. And by the way, the percentage of people that can't read it, it's like 10 or 15%. Almost everybody does, but I always have a handful of people that can't. So if you have anything that you cannot read or you can't tell symbolically what I meant, please get a hold of me right away. I can save that thing as a PDF and then repost it. I don't like doing that. It's just extra work and extra stuff. And one more thing for me to remember. And I have a very, very limited memory. You have to understand when I have to remember a new thing, that means I have to delete something from my memory because my storage is completely full right now. You know, it's the way it works. Anyway, we'll stop there.